Hello, AP Psychology. So this video, we're going to be talking about how we use statistics in AP Psychology. So if you have had AP Statistics or had any other sorts of coursework relating to it, this is largely going to be a big review for you. For those of you that have not had any background in statistics, a lot of this is going to seem like it's going really fast and it might seem overwhelming. So I'd encourage you, make sure you're seeing kind of the way that these work, and don't be afraid to do some practice and ask for help as we need it. So one thing to always keep in mind with statistics is, as hard as it is, this is how we make sense of data, because statistics are just data pieces, but then we have to interpret them to make them make sense and figure out what they're telling us, which is where we can see famous quotes like this one from Mark Twain, that there's three kinds of lies: lies, damned lies, and statistics. Because statistics are just numbers, and as we will see in our upcoming election, numbers can tell lots of different stories depending on the way that you're interpreting the numbers that you see. So let's look at how we do this in psychology, and hopefully that will help you get a little more awareness as you're starting to see statistics used to support a viewpoint, and you can see what is being said by that statistic as well as what's not being said by including that statistic. So the first thing we need to consider is, when we are keeping statistics on our data, it is critical that the data is both reliable and valid. And I will tell you, we will review this a lot when we get into our intelligence unit second semester. But as a quick introduction of validity and reliability is that validity tells us if the study or the data measured what it was supposed to measure. So that's, the study is valid if I'm measuring a certain thing and the data actually tells me about that certain thing. So for example, let's say I have a new car and I want to see how fast it can go. So I hit the gas and I hit the gas really hard. I measure how far I'm pushing down the gas pedal, and every time I push down that gas pedal to a certain distance, that car revs up to 6,000 RPMs. And then I look at the speedometer and it's not moving. Now the engine's revving up. I'm getting a statistical reading on the RPMs, but is that a valid measure of how fast the car can go? And of course it's not. So there we have a study that's not valid. I'm doing a study, I'm collecting data, but it's not measuring what it's supposed to. On the other hand, we can have reliability, and reliability is about the consistency of the data. So if I hit that gas and every time it goes to the same RPMs, that's reliable data, even if it's not measuring how fast the car actually goes. It's reliable because it's consistent every time I repeat the study. Or you can look at it and something might be valid but not reliable. Maybe you're going down a super steep hill while you were already at max speed, and you go from max speed to max speed plus 20 miles an hour. You only went that fast because you were going down a hill and gravity was helping you. So that's not a reliable method to be able to repeat my results consistently, but it's still valid because I was actually measuring how fast the car was moving. So bottom line, when we're talking about these statistics, every study we have must be reliable and valid, or else we need to question where it's coming from. So when we divide statistics at our biggest level, we have two main purposes. So the first purpose is descriptive statistics. And just as the word says, the goal here is to describe the data. And so I can give you a big fancy wordy definition and you can find a bunch of them online. But if we really cut down to it, we want to describe the data, or we want to describe certain characteristics of a population if we're talking about people. So that's where all we're doing is describing. But we also know, as we are working through the end of this unit, sometimes we want to know if one variable caused the change in another. And for that, we want to infer the cause of one variable on the other. So that's where inferential statistics come from. And the inferential piece refers to, we are going to infer from our data that our independent variable caused a change in a dependent variable. And so that's where that inferential piece comes from. So most of the time when we see statistics, they're descriptive stats. But when we see a cause stated, when we're using experiments and we're going to declare that one thing caused another, that's where inferential statistics come in. So most of these are probably familiar to you, and so I'm going to go fairly quickly through these. Descriptive statistics often use the measures of central tendency, and you need to know these first three on the screen as the measures of central tendency and be able to lump them together through that. So these are our three M's: the mean, median, and mode. So very simply, the mean is where you take all of the numbers and you add them together and divide by the amount of numbers you have. It's taking an average. And so it's very simple to do so, and it can give you just a real quick idea of what those numbers are telling you. Median is what is the middle score. So if you think of this, I like to think of the median on a highway. So it's the line down the middle. So if you take all of your data, what score falls right in the middle of all of that data? So if you get a median score on a test, that means half the people scored higher than you on that test and half the people scored lower than you on that test. It doesn't matter. You might have all gotten an A, but it still means that half the people scored lower than you because you're right down the middle. The mode is actually the easiest one to start to calculate because it's just the score that occurs the most often. And so now we can start to look into why we might use one or the other. So what we're going to see as we go into this next slide in just a second is the mean is really easily distorted. If you have a few extreme scores, the mean loses a lot of its meaning because a couple extreme scores can pull it and make it look like scores are either higher or lower than what most people really are. So the median score is telling you, okay, where's the middle? And mode scores, of course, can tell you what are most people getting on this particular thing. So if we threw out a statistic, for example, in the United States, as of several years ago, I don't have the exact year, but the average American family had 1.86 children. So again, average should be telling you that's the mean. So the average family has 1.86 children. I would challenge you to find a single family in the United States that has 1.86 children. So that data can give us an idea, but it's also a little bit strange when I talk about what does a 0.86 child look like. When we start to look at the mode, it has a little more value. The mode amount of children in an American family is 2. And so we can find families that have 2 children. And so as we start to look at it, they can all just give us slightly different perspectives. Range is just the difference between the highest score and the lowest score in this data set. So part of all these practice assignments is we will have you practice calculating these a little bit. You should know that on the AP exam, there is no calculators allowed. So any math that's given to you on the AP exam is designed to be done easily in your mind. So please keep that in mind as we're looking through that we do need to be familiar enough with these that we're not going to be running to a calculator for help. So I like to use this example of why I typically will not tell students in my 9th grade classes who don't know much about statistics. They ask about the class average and I won't tell them. Because what we can start to see is it gives them a very distorted view. Because as you can see here, the scores as they are presented, the average was a 75, but the mode and the median scores were 84. You should also see a range of 88, and on a 100-point test, that is a huge range for a test. But if we just focus on the mode and the median, those are a much better indicator of how the class did overall. And if they hear the class average, they might be a little, what's the word I'm looking for? They might be more concerned than if they said, oh, well, most people got a B and the scores in the middle got a B, but the average was a C. And we look at how does that happen? And that happens because the mean is so likely to get pulled by just a few extreme scores. So what I did in this particular data set was I included 2 scores that I call the epic fails. One person here got a 4%, one person got a 12%. And you can see if I removed those 2 extreme scores, that mean falls to an 83. which is very close to our other two means of central tendency, and our range is much lower also. But just those two scores dropped our mean score by a full letter grade. And so mean can be good if you're trying to use something, especially if there's not a wide range of scores. But it can also be incredibly deceiving if there are ranges of scores. So if we think of something like average income in the United States, and I don't have numbers in front of me, but we do know that average income in the United States is higher than it would appear, or I'm sorry, it is pulled higher because the United States has a few really, really rich people. But the vast majority of people, the median income is actually a much better indicator because that focuses on what do most people make. And we're not worried about like Jeff Bezos, and we're looking more at people that are working regular jobs. What are they most likely to be earning in the United States without that distortion from people that have billions upon billions of dollars sitting in their bank accounts? So let's look at how we can start to lay these out. What we often use when we are talking about scores is a distribution. And so what we can do is lay out and we can set scores up on a normal distribution. And that's what you're seeing on the screen right now with this bell curve. So in a normal distribution, all three scores, the mean, median, and the mode, are statistically made where they match. And so anytime in this level of class, if you're given something and says it's on a normal curve or in a normal distribution, that means the mean, median, and mode are all the same number and you can move forward that way. So what we can now see is the normal curve is designed so we can measure how frequently do certain scores occur. And so as we can look at this, we can see that we are dividing our scores into standard deviations. And we do that, again, so we can measure how close a certain score is to the norm. So standard deviation, by definition, is a measure of how much scores vary from the mean. So it tells you how close you are to the mean and how similar scores are. So if you have a very large standard deviation, you're telling us that those scores have a lot of variety. If you have a small standard deviation, you're telling us those scores do not have very much variety, or variance would be the other word that we would use instead of variety here. So if we take, for example, IQ, and IQ is normally distributed, and they adjust it on a certain frequency of time to make sure that it always stays normalized. So IQ is adjusted always on a normal distribution where your mean, median, and mode score are 100. So I'm going to try to draw a little bit on the screen here. So if we are measuring your IQ, we could have our mean, median, and the three M's, our means of central tendency, all equal 100. So that is statistically manipulated. That is the case anytime we're talking about IQ scores. So if someone tells you I have an IQ of 100, that means they are right in the middle of the general population. So what we can then do is say, well, how much do people vary in their intelligence? And so IQ scores are set with a standard deviation of 15. So what this means is if you go one standard deviation, measured here as SD, that means this score is a plus 15. So if you have an IQ score of 115, that means you are 34% higher than the person with, there's 34% more of the population will fall in that range between 100 and 115. Where we really focus in this class, though, are these big numbers on the top, so much so that I'm going to skip away for just a second and use this screen. So this eliminates some of the fluff. You can see here we have our mean, median, and mode right down the middle. And these are just two ways to look at the same set of data. So these are the exact same thing, but they're color-coded to match. So if I'm going plus one standard deviation, I'm going up 34%. If I'm going down, I'm going down 34%. But what we are usually looking at here is 68% of the population falls within 1 standard deviation of the mean. So if we look on top here, so if I go, and if we use IQ, so IQ, the middle being 100, the next score or the standard deviation being 15, that means standard deviation of -1 is an 85, a standard deviation of +1 is 15. And if you're confused, I added 15 here to the mean, and I subtracted 15 here is where those numbers came from. And we know, because of what they've decided on a normal distribution, that 68% of the population fits between an IQ of 85 and 115. So that statistically is what we call normal. And a normal distribution, it's about what 68% of the people are doing. As we go to where scores occur less frequently, and we can see that y-axis shrinking as we start to go further out. 95% of the population falls between -2 and +2. So again, if we add another 15 here, if we take away another 15 here, this means 95% of the population falls between an IQ of 70 and 130. Sorry for the sloppiness. I'm trying to draw with my mouse while I'm talking. So that's 95% of the population. If you keep going to one more standard deviation, now we should know that's 55 and 145, 99, and if we go really specific, 99.73% of the population will fall between the IQ score of 55 and 145. And that's why we use these. You should memorize the 68, 95, 97, I'm sorry, 68, 95, 99 rule. You should have that burned into your brain. That is something that you are just expected to know and might have to make calculations from. Again, nothing hard in AP Psych Math, but it is something where if someone says, hey, you are at this level, what is the standard deviation here? Another thing we might often see here is a z-score. And so a z-score, very simply, is the same as the standard deviation score. It's just another label for that. So if you ever end up with a professor in college who grades your scores on a z-score, and some do, I had several that gave me a z-score back, and you had to understand how this works. So what that means is if you get back a z-score of 0, that means you're right smack in the middle. You got the average of everyone in the class. If you get a z-score of +1, good job. You did better than most of the students in the class. It's about 84% if you add up all the numbers. We have, this is the top half, we add 34 more, and that's 84% you did better than. We might also refer to that as a percentile score as you are starting to go up. So the standard deviation or z-score of 1 is an 84th percentile. If you got a z-score of +3, congratulations, you probably had the single best test score in that group. If you had the z-score of -3, sorry, you had the worst score in that group. So generally what they would do if you're truly doing a curved test score is you're gonna say, here's where my average should be. I think my average should be an 80% on this test, so I'm gonna move our average to that, and then start to mess with standard deviations to determine what your score should average out to on a curve. And that's more complicated of a process than we want to get into in this class. But know if you ever hear grading on a curve, that's actually what it's doing if it's being done properly. One thing you have to be able to recognize, and we're not going to spend a lot of detail on here, but it does show up from time to time. A lot of times real data doesn't work so nicely with the mean, median, and the mode all in the same line. So that's a normal distribution, but sometimes data gets skewed. When data gets skewed, it's where the mean, median, and the mode do not line up. It's when that mean is extreme and it's starting to pull scores one way or another. So the easy way to consider this is you're looking at this diagram. A negative skew, the little tail drops down and points in the negative direction. A positive skew points in the positive direction. So just if we give you a real quick example of this, if we would say, for example, a negative skew, let's say someone gave you a super easy test. The average, I'm sorry, not the average score, most students got a 90% or higher, but there were a couple that failed, like our example we showed you earlier. The mean is lower than the mode, and so the data will show up as a negative skew. On the other hand, a positive skew could be something that we saw where maybe if we're calculating incomes in the United States, the mode and the median scores are lower than what the average would be when you start to include that there's a few people like Jeff Bezos that just have a whole lot of money out there that's going to skew the data in a positive fashion. And so really anytime I've seen this on an AP exam, it just asks you to identify it. Is this a positive skew? Is it a negative skew? And know that the mean is usually the one that's on that lower end than the mode and the median. So now we get into inferential statistics. And as we started to say at the beginning of this video, inferential statistics are about inferring cause. I need to know that one thing caused another thing to happen. And so I'm inferring that one variable caused the change in the other variable. We measure this as a p-value. P standing for probability that the results were due to chance. So make sure you let that sink in, that this is the probability that the results were due to chance, because that's always the threat. When we are measuring experimental data, what if this was just a fluke? What if that one weirdo ended up in the group and now the data is showing one thing, but it wasn't actually the variables that did it? And so there's all kinds of fancy calculations that we don't need to worry about at this level of the course, that you come up with a p-value. In this class, what's going to happen is you're going to be presented with a p-value, and you're going to have to tell me, what does that mean? And so what psychology has agreed upon is, well, of course, the lower p-value, the better. So a low p-value means that there's a low probability that the results were due to chance, and a high probability the results were due to the independent variable causing the change in the dependent variable. So what we have agreed is we will call data statistically significant if that p-value is 0.05 or lower. So if a p-value ends up at 0.05 or lower, what you're saying is there is a 5% chance that the results in my study were just due to random events of chance. And there's a 95% chance that the independent variable was the influencing factor on the change in the dependent variable. So that's what statistical significance is always referring to. I would like to point out, I gave you on our unit outline two specific phrases that you should memorize word for word. So when you see statistical significance show up on a FRQ at some point, and you will, it's on most of them, that you need to know that when you're writing that, you are talking about how if data has been shown to be statistically significant, it means there is a high probability that the independent variable caused the change in the dependent variable, and a low probability that those results are due to chance. So that's what we're going for. And of course, when we replicate, we're going to continue to see this. Sometimes a study might have a piece of data with a low p-value. Remember, low is good when we're talking p-values, but then it's replicated and the p-value gets higher. So in that case, when we have a replicated study, particularly if it has more people, so it's a more valid study, then we have to revisit how those p-values were calculated and see which one is more valid. And again, that's beyond what we need to do, but it helps with that understanding of what's the p-value telling us. So sometimes we make errors. And so as we're working through this, we can end up with a type 1 error or a type 2 error. So a type 1 error would occur if it's a false positive. So you think the independent variable changed the dependent variable, but it was actually chance. So maybe your p-value came in at a 0.04 and you're like, there's a 4% chance it's due to chance. And as you run some more studies like that, you realize, oh, that was a type 1 error. It actually wasn't my variables, it was just random. Or you can have a type 2 error, which is the exact opposite. You think your findings are due to chance. You give yourself the p-value of, like our mug here, a 0.06, but you find out as you replicate studies later, it actually was the variables. And so here's a good way I have to remember this. I pulled this out of an old psychology textbook as a great way to help us remember what are the differences between these two variables, or between these two types of errors. So the type 1 being the false positive, as you can see here, and the type 2, once again, being false negative. So one thing that I would like you to work towards, I have an assignment on Google Classrooms now about statistics practice. I would like you to take a shot applying the knowledge from this video and your readings. You're going to do some basic calculations, and you're going to be doing some inferring of what can we interpret from this data. They are designed to be challenging, and that's okay. So I want you to know that if you're struggling, that's okay. There will be another video to help walk you through them, but I want to make sure that you try them first so that hopefully you're just double checking your answers and your ways of thinking. We don't want you to rely on it because it's not going to be there to rely on in the future, but I've seen that we need enough support on this, especially for students that are new to statistics, that I wanted to give you that support as you're working through this for the first time. As always, please reach out if you have any questions or concerns or need any other support throughout this course. We'll see you all soon.